Okay, I can't promise that it's going to be much better because there are people out in the very front working on the road, but hopefully the dogs have gotten tired of barking at them. We will see how that goes, okay? All right, so we just saw the growth of bacteria, so now let's look at some decay. And the best way to look at decay is with what we call radioactive decay. So radioactive elements like plutonium, sorry, I'm trying to think of like, making bombs and nuclear power plants, but plutonium, even iodine, potassium, what these elements do is if you've got a clump of plutonium in your hand, which obviously would kill you, but if you've got a clump of plutonium in your hand and you hold on to it for a long period of time, just by being in nature, it's going to start to decay, which means it's going to start to let off parts of it, and it gets smaller and smaller and smaller. Now, in most cases, these elements, like if you have a clump of plutonium, it's going to take millions of years for you to even notice that the size has changed. Okay, potassium, I think, is billions of years. So it's a slow process. But some of them aren't as slow. Like iodine is a much faster decaying element. So if you have a clump of iodine in your hand, after, let me just look real quick. 8 days. So after 8 days, you'll have half the amount that you had originally. So it's gonna just kind of let itself go into the air. And that's why it's honestly so bad, is because as it's decaying, all those little particles end up inside wherever you are. Some obviously are worse than others. So radioactive decay is a good way to look at the decay function. And everything has every living thing has carbon in it, and carbon is another one that decays. So your bones have a particular amount of carbon. Now, when you die, your bones are going to start to let off that carbon. They're going to decay a little bit at a time until they fully become fossilized. And if we find those bones, if we can check how much of the original carbon is still in there, then we can tell people how old the bones are. And that works a lot for like cold case murders. When it comes to looking at bones of dinosaurs, though, the carbon has decayed too much. So what we have to do is we have to look at like the rocks around it and see how those rocks are decaying. So, but it's a good way to figure out length of time by knowing how long it takes for the radioactive isotope to decay. Okay, so there's again my little science spiel for you. So the formula is the same. The formula does not change. So what we are going to do is we're going to do number 4, and we're going to write the decay formula. So I'm going to put that up here. Let's write the decay formula. Okay, so number 4, and it says, a dinosaur bone is dated by establishing the age of the rocks surrounding it using potassium argon dating, which has a half-life of 1.31 billion years. So potassium argon has a half-life of 1.3 billion years. Okie dokie. So again, if you have a clump of potassium argon in your hand, then it will take 1.31 billion years for that clump to be half the size that it originally was. So it's decaying, but it's decaying very, very, very slowly, okay? All right. So this then says, if the rock has 94.5% of the original potassium argon, how old will the dinosaur bone be? Okay, we're not gonna focus on this yet. We'll come back to that. We're going to use just that first part with the half-life. We're going to use that to write our decay function. So we're gonna plug in the pieces we know in the spots that we know, using, again, whichever format you like better, whichever letters. So here's the thing though. I said a clump. Okay, you have a clump. All right, well that's your starting off. And we can't really write the word clump there, but let's say that it's one clump. Then if we're looking at half, at the end of this amount of time, won't there be half a clump? So later we're gonna have half a clump, but we started with one clump. So one and then half. And then we're gonna go E, but here's the dealio. We don't know the K. They didn't tell us the K, they told us how long it would take. So we're gonna go K times 1.31 billion years. So that's gonna be 13100000000, right? Thousands, millions, billions. Okay, 1.31 and a bunch of zeros. Now, this looks like a problem that we were doing in the sections before, solving this for K. So that's what we're gonna do. We wanna get the E alone on this side, so we would divide by 1. That's not gonna change anything though, is it? So we still have 1/2 equals E. I'm just gonna write it the other way because that's the way we're used to seeing it, with the K at the end. Okay. All right, so now, this is where we're gonna go over to log form. So we're gonna start here with our base, which is gonna be ln, right? Log base E, come across the equal sign. So the ln of 1/2 will equal this big old number. 131, 1, 2, 3, 4, 5, 6, 7, K. So then, can we divide by this big number? 1, 3, 1, blah, 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 blah. But we're gonna have to divide this side as well. 1, 3, 1, 1, 2, 3, 4, 5, 6, 7. And this should tell us what K is equal to. What do I do with my calculator? Okay, so we're gonna go clear it. We're gonna go ln, and I would just do 0.5. Why do 1/2 when you can just do 0.5? And I'm gonna hit enter first. Then I'm gonna divide by the big number. 1, 3, 1, 1, 2, 3, 4, 5, 6, 7 equals. Okay. So hopefully you got a really teeny number. Mine is in scientific notation, yours probably is too. So we've got, wait a minute. $1.31 billion years. Okay, let me do it one more time. So ln 0.5 equals divided by 1.31, 1, 2, 3, 4, 5, 6, 7. Okay, so I got negative 5.29 times 10 to the negative 10, which seems like an incredibly ugly problem. I don't know why they chose this one as your first problem, but so they're saying that our K is equal to negative 0.00000000090 Okay, let me just tell you, this came out of the book. I did not make this up myself. So there is a very, very teeny weeny rate, but we've got it. So we can write our formula for the decay of potassium argon. We can say that N is equal to N sub 0, because we don't know how much potassium argon we have, okay? E to our new rate, negative 0.00000009 T. All right, so if anyone ever asks you to do some potassium argon dating, you go, hey, I actually came up with that formula. Now, from here on out, anytime anyone asks us, this is our formula. So the next part of the problem says our rock has 94.5% remaining. Let's use the word remaining. Remaining. So we know how much we have over here. Now, again, we're not talking in clump, we're talking in percentage. So if this side is 0.945 in decimal form, the original was 1 clump. So this is 1. We have 1 clump, and then our big 0.00000000529 T. Okay. Now, we can do the same thing and work our way backward with the natural log so that we can solve for T. So let's see what we get here. If we get rid of the 1 because we really don't need it, we're going to go again like this around, and we're going to say ln of 0.945, I can't believe I have to write this again, is equal to negative 0.000000000529 T. And one last time, let's divide by this big 0, blah, 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 blah. Divide by it over here, negative 0.0000000529. And let's figure out what T equals. Holy crap. What a problem to work with. All right, so ln 0.945 equals divided by negative, not the subtraction, the negative sign, 0.123456789 106,938,282.6 years. Okay, so what popped out of my calculator was a little, almost 107 million years. So this dinosaur bone is 107-ish million years old. And we got that by checking the rocks around it. Okay, kind of a tedious little thing, but the process is using that, the natural log to get back out of the exponential, so we can either calculate what the K is or what the T is, depending on what you're looking at there. All right, how are we doing time-wise? Don't want this one to go too long. Okay, let's do one more here, and then we're gonna do the turkey problem on another video. Okay. Okay, so let's erase this crap. Okay, so this one I didn't mean to do, but because this is such a long process, I want to try it again. So I am going to write this one up here. What happened to my blue pen? This is working for me. Where did I put it down? Seriously, where did I put it down? Oh, come on, blue pen. That is so weird. There's like no other place for me to put it down, but I apparently lost it. All right, let's go with this orange pen, see how this works. Okay. So this one is iodine 131. And iodine 131 is a radioactive isotope that is commonly used to detect how well the thyroid is functioning, for thyroid function. Okay. Suppose the decay of iodine 131 follows the model given in 6.5 and has a half-life of 8 days. So this has a half-life of 8 days. We are going to find the decay function. Now, every doctor that is dealing with thyroids already knows the decay function, okay? Already knows the decay function. But this is the way that they originally found it. So now we are going to find it again so that we could give it to the doctor and say, this is the function that you use to check how well the thyroid is working. Okie dokie. So all we need to do this is the half-life, and that's it. So I know I erased the formula, but we're going to end up with half of the original. Remember, original goes here, and what you have left goes over here. So we started with one clump. We're going to have half a clump later. Then comes the E to the KT. Now here we're missing the K, but we know that T, and this one is different, it's not in years, it's in days, is 8. So we don't need to divide because it's just dividing by 1, so we can just get rid of that 1 there. And we're going to go across the equal sign and back around. So we're going to say ln of 1/2 equals, and I'm just going to write it as 8k. And then we can divide by 8. Okay, so when you're not dealing with a whole bunch of zeros, it's a lot easier to do. Okay, I don't know why they chose that one as your first example. So that means k is going to equal, and again, we're going to go ln 0.5 and then divided by 8. And here, it's always going to be negative because it's decaying, so that the rate is going to be going down, so it's negative. And I've got 0.08, let's go 0.0866. Now, that means that we have the rate and we can write the function. So the function then looks like n equals n sub 0, because this part of the function we don't know what is happening yet, e to the negative 0.0866t. Now, this radioactive isotope is given to a patient, and then the thyroid is supposed to take care of it, is supposed to decompose it or whatever. So it helps to see how the thyroid is working or not working. So in this example, it says, if 5 grams is given, and then what does it say? It just asks how much will be present in 10 days. So they can ask you a bunch of different questions. In this case, they just want to know how much is present in 10 days. So they're asking you to plug in the pieces and then come up with the n here. So in this case, we start with n over here, but this is our initial value given. That's our 5 grams. And then we go e to our negative 0.0866, and we hit it with our t, which in this case is 10. Now remember your parentheses here, so if we go 5 and then E, negative 0.0866 times 10, close the parentheses, and I got N is equal to 2.1 grams. Okay. Anyway, so there is a formula that the doctor can use when testing thyroid functions. More than that, I really don't know, but I know that much. Okay, look good? Let's stop there. So work through some of these problems on your own, and then remember, if you get caught on something, just ask a question. I'll be happy to help you out.